Have you ever looked at something like gold and wondered, why is it so shiny? Or, why does a tiny piece of sodium go crazy in water? Well, the secret to all of that, it's hidden inside every single atom. It's like a secret blueprint, and it's called an electron configuration. Today, we're going to learn how to read that blueprint and understand the rules that literally build the world around us. So to get our heads around this, let's use a little analogy. I want you to picture an atom as a giant apartment building, and the electrons, they're the tenants. The big question we're tackling today is, where do all these tenants live, and how do they decide which apartment to take? That's what we're about to figure out. All right, here's our plan for today. First, we're going to figure out an electron's mailing address. Then, we'll cover the strict rules of the house they all have to follow. After that, we'll actually build a few atomic neighborhoods, check out some weird quirks in the blueprint, and finally, see how this whole thing unlocks the biggest cheat sheet in all of science, the periodic table. Okay, let's jump right in with part one, the electron's address. Just like your home address tells people exactly where to find you, an electron configuration is a super specific code that tells us exactly where each electron is hanging out inside the atom. So what is an electron configuration? Well, at its core, it's the atom's master plan. It shows us the exact arrangement of every single electron. But it's so much more than just a list. This arrangement is everything. It determines an element's personality. Is it reactive? Is it stable? It all comes down to this blueprint. Let's break down that address. The very first part is the principal shell, which we just call N. In our apartment building, this is super simple. It's the floor number. So an electron in the N equals 1 shell is on the first floor. N equals 3, third floor. And just like in a real building, the higher you go, the more energy it takes to get there. Next up, we've got the subshell. This is shown by one of 4 letters, S, P, D, or F. So going back to our building, you can think of these as the different apartment styles available on each floor. The S subshell is like a simple, spherical studio apartment. The P, D, and F subshells, they're the more complex, multi-room layouts. And the last piece of the puzzle is that little number written up top, the superscript. This one's easy. It just tells you how many electrons or tenants are living in that specific subshell. So if you see 2p4, it just means you've got 4 tenants living in the P-style apartments on the second floor. Simple as that. Now, you might be thinking electrons can just move in wherever they want. But nope. Just like any good apartment building, this one has a very strict landlord and some non-negotiable house rules. There are 3 big ones that dictate exactly how our electron tenants find their homes. Rule number 1 is the Aufbau principle. It's German for to build up, and it's all about efficiency. Electrons are lazy. They always fill the lowest energy spots first. In our building, this means new tenants are going to snatch up all the cheap apartments on the first floor before anyone even thinks about moving up to the second. Next, we have the Pauli exclusion principle. This rule is fascinating. It says that no 2 electrons in an atom can be exactly identical. So what happens if 2 electrons have to share the same orbital, the same room? Well, they have to have opposite spins. Think of it like 2 roommates who can only get along if they have completely opposite personalities. And the third and final rule is Hund's rule. I like to call this the rule of personal space. Let's say you have a P subshell, which has 3 empty rooms all at the same price. Hund's rule says that new tenants will each take their own private room before anyone is forced to double up. I mean, it makes sense, right? Don't get a roommate until you absolutely have to. Okay, so we've got the address system and we know the house rules. It's time to put on our hard hats and become atomic architects. Let's see how this all plays out by building a few elements right from the very beginning. So just watch how the rules work together here. Hydrogen has 1 electron, so it goes to the lowest floor, 1s. That's the Aufbau principle in action. Now helium adds a second electron. It goes into that same 1s room, but see, it has an opposite spin. That's the Pauli exclusion principle. With lithium, the first floor is full, so its third electron has to move up to the second floor into the 2s apartment. And then look at carbon. It's the perfect example of Hund's rule. Its 2p electrons each take an empty room before they'd ever consider pairing up. All right, so those rules seem pretty solid. But like any good story, there are always a few plot twists. It turns out that in the complex world of the atom, there are some really interesting and predictable exceptions to the rules. So here's probably the most famous quirk of them all. Logically, you'd think the third floor apartments, the 3D ones, would fill up before the fourth floor. 4s, right?
But it's not that simple, because of some complex physics involving something called shielding. The 4S apartment is actually at a slightly lower energy level than the 3D ones. So believe it or not, our electron tenants will move into the 4th floor before they fill up the 3rd. Weird, I know.
And this little quirk leads to some really cool anomalies. Let's take the element chromium. If we just follow the rules blindly, we'd predict it should have 2 electrons in its 4s orbital and 4 in its 3d. But when we actually look at a real chromium atom, that's not what we see. We see 1 electron in 4s and 5 in 3d. So what on earth is going on? The whole reason for this comes down to one single powerful idea: stability. See, atoms, just like everything else in the universe, are always seeking the lowest, most stable energy state they can possibly find. And it just so happens that having a subshell that is perfectly half full or completely full creates this extra stable, super balanced condition. The atom wants this stability so badly, it'll actually break the standard filling rules and promote an electron just to achieve that perfect symmetry. So we've gone through the rules. We've even looked at the exceptions. Now it's time for the grand finale, the big picture. Because this whole system isn't just some abstract idea. It is the secret code that organizes the single most important chart in all of chemistry, the periodic table itself. Now, to really get this, we need one last piece of vocabulary: valence electrons. These are the electrons in the outermost shell, the ones with the highest energy. In our building, they're the tenants living in the penthouse suite. And they are the most important electrons of all because they're the frontline soldiers that actually go out and interact with other atoms. This quote absolutely nails it. Every chemical reaction you can possibly imagine, from a roaring fire to the quiet chemistry happening inside your body right now, it's all dictated by these outermost valence electrons and what they decide to do, whether they're lost, gained, or shared. And here it is. This is the big secret, the aha moment. Ever wonder why all the elements in the same column of the periodic table act so similarly? Well, now you know. It's because they all have the same number of valence electrons. The periodic table isn't organized alphabetically or by discovery date. It's a perfect map of electron configurations. It's a family portrait of chemical behavior. So we'll end on this thought. We started out just asking where electrons live. But along the way, I think we found something much more profound. An electron configuration isn't just an atom's address. It's a deep look into its personality, its stability, its willingness to react, and its incredible potential to bond with other atoms and create, well, everything we see.